Somewhere between the sun and Earth right now, a cloud of charged solar material is racing toward our planet. The scientists tracking it are being unusually honest about something most space weather coverage glosses over. They genuinely don't know yet exactly how hard this one is going to hit. Unlike the big, dramatic solar flares that come with a clean, instantly classified signature, this particular storm traces back to a quieter, sneakier kind of solar eruption, one that forecasters openly admit is far harder to read in advance. Today, we're going to break down exactly where this storm came from, why this specific type of solar event keeps catching modelers off guard, and what that genuine uncertainty actually means for anyone hoping to see the aurora, or anyone running a satellite, over the next few days. Let's start with what's actually been happening on the sun this week, because the story builds directly on top of it. A few days ago, a long-duration flare erupted from an active sunspot region on the solar disk, coinciding with a filament eruption nearby, together launching an Earth-directed cloud of solar plasma. Forecasting models placed its arrival early on the 2nd of the month, and right on schedule, Earth's magnetic field responded, escalating from calm, quiet conditions into a full, moderate geomagnetic storm within just a matter of hours. The planetary KP index, the standard scale scientists use to measure how disturbed Earth's magnetosphere is, jumped from near 0 all the way up to 6, comfortably into G2, moderate storm territory, and skywatchers across northern Scotland and Scandinavia reported aurora, even with only a few hours of true summer darkness to actually see it in. That storm, on its own, was well forecast, and behaved almost exactly as predicted. But then came what happened next, and this is where the real story of this week begins. Over the following days, flare activity on the sun actually dropped to very low levels, barely a handful of weak, minor eruptions. And yet, almost as if the sun found a quieter way to stay busy, several separate filament eruptions tore loose from the solar disk in quick succession, each one hurling its own cloud of plasma out into space. As of the most recent update available, space weather forecasters are still working through the modeling on these newest eruptions, openly acknowledging that they don't yet know for certain whether, or how, directly, any of this fresh material is actually heading toward Earth. Here's why that uncertainty is genuinely different from a normal forecasting gap, and not just scientists being cautious for the sake of it. Think about what a filament actually is. It's a long, rope-like structure of relatively cool, dense plasma suspended above the sun's surface by twisting magnetic field lines, visible as a dark, snaking line when it's silhouetted against the bright solar disk, or as a bright loop of material when it appears off to the side against the darkness of space. Filaments can sit quietly for days or even weeks before their supporting magnetic structure finally becomes unstable and lets go, and critically, that collapse doesn't always come paired with the same kind of loud, easily classified X-ray flare that accompanies eruptions from active sunspot regions. A big flare from a numbered active region gets picked up almost instantly by X-ray sensing satellites, and immediately assigned a letter and number, C, M, or X class, based on its exact radiation output. A quiet filament eruption can happen with comparatively little of that same clean signature, which means forecasters sometimes only fully register that an eruption has happened after the material is already well on its way into space, rather than catching it the moment it lifts off. Think about what that actually means for anyone trying to predict where there's a resulting cloud of plasma is headed. Space weather forecasters rely heavily on a tool called the WSA-Enlil model, which takes measurements of a CME's speed, width, and direction as it leaves the sun and projects forward to estimate when and how forcefully it might reach Earth. Even with a clearly observed eruption, these models routinely carry real uncertainty, sometimes reporting confidence levels for a specific arrival scenario in only the range of 50%, with lead times as short as 6 to 20 hours between when a prediction is finalized and when the actual event is expected to hit. With a filament eruption, where the initial launch itself is often less clearly observed, that already meaningful uncertainty compounds further. If you're finding this breakdown useful, go ahead and hit that like button. It genuinely helps this kind of science coverage reach more people who are actually curious about how forecasters try to predict something this genuinely difficult to pin down. It's worth walking through who actually feels the difference between a routine pass and a genuine surprise, because the stakes aren't purely academic. For satellite operators running spacecraft in low Earth orbit, a stronger than expected storm heats and expands the upper atmosphere more than models anticipated, increasing drag and occasionally forcing last-minute orbit adjustments to avoid a closer than planned pass with another object. For power grid operators, particularly at high latitudes across Scandinavia, Canada, and the northern United States, a storm that outperforms its forecast can push geomagnetically induced currents higher than planned for, prompting operators to adjust transformer loads on short notice rather than during a calmly scheduled maintenance window. Airlines flying polar and transoceanic routes watch the same uncertainty closely, since a storm that arrives stronger than expected can degrade high. Frequency radio communication with little warning, occasionally forcing a route change. Mid-flight rather than one planned well in advance. None of these consequences are catastrophic on their own, but all of them are meaningfully easier to manage with accurate advance notice, which is exactly the piece a filament-driven storm makes harder to guarantee. There's an even deeper layer to why a storm like this can still surprise everyone right up until the very last minute. Even once a CME has been tracked most of the way across the roughly 93 million miles separating the Sun and Earth, the single most important detail determining how strong the resulting geomagnetic storm will actually be, the orientation of the magnetic field embedded within the CME itself, generally can't be measured with real confidence until the cloud sweeps directly past monitoring spacecraft stationed at a gravitationally stable point roughly 1 million miles from Earth, directly in the solar wind's path. If that magnetic field happens to point south, opposite to Earth's own northward-pointing field at that location, it links up efficiently with our planet's magnetosphere and dumps far more energy into the system, driving a stronger storm. If it points north instead, much of that same CME can sweep past with barely a ripple in geomagnetic activity. That distinction is often only knowable somewhere between 15 minutes and an hour before the material actually reaches Earth, which is precisely why a forecast that reads as a routine, minor disturbance, 1 hour can suddenly escalate into something considerably more significant the next. This isn't a hypothetical concern either. Space weather history already includes a genuinely stark example of forecasts being outpaced by reality. Back in May of 2024, a series of X-class flares and multiple coronal mass ejections from a single, unusually complex sunspot region combined to produce a G5, extreme-level geomagnetic storm, the strongest recorded since 2003, and a statistically rare event researchers have since described as roughly a 1 in 41 year occurrence based on its overall duration and intensity. Solar wind speeds during that event ultimately reached somewhere between 750 and 950 kilometers per second, and the resulting aurora became visible across an extraordinary range of latitudes, seen clearly across much of North America, Europe, and even parts of Australia, regions that essentially never see the aurora under normal conditions. That event stands as a genuine reminder that even with today's monitoring network, the Sun retains a real capacity to exceed what forecasters initially expect once a major eruption is actually underway. To be clear, nothing currently being tracked this week suggests anything remotely close to that scale of extreme event. The active region responsible for this week's confirmed storm has been producing moderate M-class flares rather than the powerful X-class eruptions behind the 2024 event, and the newest filament-driven material still being analyzed is, so far, an open question rather than a confirmed major threat. But that's precisely the point being made here. The gap between routine and remarkable in space weather often isn't obvious until the moment a CME's true magnetic orientation finally reveals itself, sometimes with less than an hour of genuine advance warning. If storm coverage like this is something you want more of the moment new activity develops, subscribing means you'll catch the next update as soon as forecasters have a clearer picture. Zooming out from this particular week, it's worth remembering where we currently sit in the Sun's longer 11-year rhythm of rising and falling activity. Solar cycle 25 has already passed through its peak years, but elevated activity like this, multiple filament eruptions within days of each other, layered on top of an already confirmed moderate geomagnetic storm, remains genuinely common during this stretch of the cycle, rather than some rare standalone anomaly. There's also a real technological upside worth mentioning here. Newer monitoring spacecraft positioned at that same gravitationally stable point ahead of Earth now carry improved instruments capable of detecting CMEs somewhat earlier in their journey than older equipment could manage, giving forecasters incrementally more lead time, even when a specific eruption's origins were murky to begin with. That upgrade doesn't eliminate the fundamental physics driving this uncertainty, since the magnetic orientation of an incoming cloud will likely always remain difficult to pin down until it's genuinely close, but it does mean the window for reacting to a surprise has grown slightly longer than it once was. For anyone in higher latitude regions hoping to catch the aurora over the coming nights, the honest guidance right now is to watch real-time updates rather than committing to plans based on forecasts issued days in advance, precisely because the strength of whatever arrives could shift meaningfully in either direction right up until the final approach. Based on this week's already confirmed moderate storm, realistic viewing chances extend across northern Scotland, much of Scandinavia and the northern tier of the United States and southern Canada, with the exact southern edge of that visibility line entirely dependent on how strongly and in what magnetic orientation any newly tracked material actually arrives. For satellite operators and grid engineers, this kind of stretch is a familiar one, a period of elevated but genuinely uncertain risk that calls for close monitoring rather than alarm. It's also worth being direct about what this uncertainty does not mean, since headlines built around words like surprise tend to invite exaggerated interpretations. Nothing in this week's activity points toward anything resembling a Carrington-level event, the kind of historically extreme storm capable of widespread infrastructure damage. Even the most intense plausible outcome sitting within current model ranges would land somewhere in the moderate to strong category, disruptive for specific sectors like aviation and satellite operations, but not remotely close to the kind of society-wide disruption that occasionally gets implied in more sensational coverage of space weather. The genuine uncertainty here is about degree, not about whether this event belongs in some entirely different, far more dangerous category. Bringing this all together, what makes this particular storm worth paying attention to isn't a single dramatic number or a guaranteed spectacular outcome. It's the genuine, honestly acknowledged uncertainty sitting at the center of the forecast. A filament eruption without the same clean early signature as a major flare, a magnetic orientation that won't reveal itself until the cloud is nearly here, and a recent history that includes at least one storm dramatically, outpacing what anyone expected, all combine into exactly the kind of situation where the most accurate thing scientists can say right now is also the most interesting one. This storm racing toward Earth might turn out to be a quiet non-event, arriving with a northward-pointing field that slides past our magnetosphere with barely a ripple. It might also turn out to be something considerably more active than the current models suggest, arriving with a kind of southward orientations that unlocks a far stronger response. Right now, being honest about not yet knowing which of those outcomes is coming is exactly what responsible space weather forecasting looks like, and it's exactly why scientists tracking this one are watching their screens a little more closely than usual over the next day.